I made this video to talk to you a little bit about probability bounds. The topics that we are going to discuss in this video are very important and very useful things to have in your toolbox when, let's say, writing a paper, reading one, or contending with materials in data science, machine learning, and statistics. Namely, considering a random variable z, where we know the expectation of z is the EZ, the question that is important is how likely it is for z, the random variable, the value for it, to be close to the expected value of it. In other words, if you consider a distance t from this expected value, like let's say t is a positive value, what is the probability of the value of this random variable being more than t away from the top, let's say from EZ, or more than t away from the bottom from EZ? And these basically we want to find some formulas that can help bounding probabilities of these two events. Note that these two equations would pertain to z minus ez in the abs notation be larger than or equal to t. For example, if you have a Gaussian distribution like this and the average of it or its peak point is here, and if you consider a t, let's say this average is 0 and therefore this is t and this is minus t, we want to basically consider the area underneath these two sections, assuming that this is a probability distribution. So any sort of distribution that has a mean, we sort of want to see how likely it is for the z to be close or in the whereabouts of EZ. The first bound that we want to talk about is the most famous Markov's inequality. Consider z be a non-negative random variable, meaning that the values of z, even though random, are larger than or equal to 0. Now consider a positive real valued number t. The probability of this z being larger than or equal to t is less than or equal to E of z, expected value of z, divided by t. Now it's a very useful theorem. Let's try to prove it. Consider the probability of z being larger than or equal to t. You could write it as expected value of z basically being sampled from this probability distribution, expected value of this 1, this is a indicator function, meaning that it's 1 if this condition holds and 0 otherwise. So you can consider this basically being the probability of every z times the indicator of whether or not that z is larger than or equal to t, and it's summed over everything. So basically it would amount to the probability of z being larger than or equal to t. Now with that in mind, z being larger than or equal to t is an event. What that means is that if this event is true, meaning if z is larger than or equal to t, z divided by t is going to be larger than or equal to 1. And note that given this here was an indicator function, 1 is larger than or equal to its output value. So we're going to do a trick here. From these two, we know that this value over here, which basically was equal to the p of z larger than or equal to t, is less than or equal of the expected value of this indicator function, and we would put this instead of the indicator function. So it would be less than or equal to, instead of this indicator function, we would put z and t, and given that t is independent from z, it comes out of the expectation, and therefore you will have the p of z less than or equal to t is larger than or equal to t is less than or equal to Ez divided by t, which proves the Markov's inequality. The second thing that we want to talk about is Chebyshev's inequality. Consider z being a random variable, and consider that the variance of z is bounded, meaning that if v is the variance of z, is less than infinity. If you pick any real valued positive number non-negative number t, the probability of z being larger than or equal to Ez plus t, or this is a disjunction, and or the event of z being less than or equal to Ez minus t, or intuitively, the probability of z not being close to Ez by the margin t is going to be less than or equal to the variance of z divided by t2. This is pretty similar form to Markov's inequality, and all of these bounds that we want to talk about have some sort of this, similar looking forms. Now let's try to prove it. To prove it, we can use Markov's inequality. So the way you do it is this. Note that you can write the condition above, basically this condition over here, given that it's basically the absolute value of z minus Ez, you could write it and like this, which is just the squared form of that. So you have z minus ez to the power of 2 is larger than or equal to t2. Now, this probability over here, this event, is the same as this event, right? So if you put it like this, you will have this newly formed like random variable and newly formed threshold t. So you can now use the Markov inequality in which the previous t is now t2, which we put it here, and the previous e is now e of this new random variable, which if you put it like this here, you will end up with expectation of z minus ez to the power of 2, which is by definition the variance of z, which therefore proves Chebyshev's inequality in its general form. An important corollary of this is that if you consider random variables with finite variance and you average them, let's say a lot of them, it's going to converge to its mean. For example, say z1 to zn are independently sampled from a distribution, and let's say the average of them is 0 for easier writing. If not, you can basically do it like this and you have the same thing, meaning that if you have a random variable and if you define another random variable which is defined by z minus ez, the new random variable will have the expected value of 0. So let's define z bar like this. It will be you take n random variables, zi's, and then you define the new random variable z bar by basically averaging them. Now the variance of z bar, if you want to compute it, it becomes like this. You will have the expected value of 1 divided by n2. You bring this factor out, and remember that the average of all of the z's was 0, therefore the average of this would also be 0. And then you would put the zi there, and you, with this distribution, you will get e of 1 divided by n2 times this summation. So summation over, again, you have z1 plus z2 plus all the way to zn times parentheses z1 plus z2 all the way to zn. Therefore, for any combination of I and j, you have a zij term. Note that in this case here, I and j both can have any value between 1 to n, and this covers the whole thing. So noting that these are independently sampled, and you look at this expectation, you can again have this out of the expectation and this out of the expectation, and you will end up with this, meaning that you have 1 divided by n2 times the summation of I from 1 to n, e of z2, which by definition would be equal to the variance of z1 divided by n. So to sum it up, for any positive t, you have this term, which is the same as the probability defined above, meaning the empirical average of these zi's being larger than or equal to t, given that e of each one of these zi's was 0, is less than or equal to variance of z divided by nt2. This is basically the corollary. Now we know that if we take a limit of this and approach n to infinity, this would basically approach 0 positive. So yeah, so we can see that the results would converge to its average. Now we want to talk a little bit about moment generating functions. So a moment generating function for z with input lambda is going to be the expectation of e to the power of lambda z. And this can help us with defining sharper and better bounds. Now let's talk about Chernoff bounds. Consider z being a random variable. For any t larger than or equal to 0, we have the probability of z being larger than or equal to z plus t. By the way, this is the expected value of z plus t, is less than or equal to this term over here. So if you look at this, let's kind of segment this different components. You have e minus lambda t. Note that t and lambda are there. And then this term here, which is e of lambda z minus ez. And note this min term over here. Which now, if you consider this being the random variable of yours, you could consider that min of lambda larger than or equal to 0 times moment generating function of z minus ez lambda times e minus lambda t. So based on this moment generating function's definition, you could write this bound like this. Now we want to see why this is true. So again, we have the similar thing for ez minus t, so kind of diverging from below that number. And we again have the same term with the exception that now we have ez minus t, given that z is below average. To prove that, we could focus on proving the first term. The other one is identical. Okay, so the first thing to note is that x is an increasing function. Now, let's pick the event of z being larger than or equal to ez plus t. Now, in this term, if you consider the e to the power of lambda z, given that z is larger than this number, this results in that e to the power of lambda z is larger than or equal to e to the power of lambda ez plus lambda t. Note that lambda was also positive, but it doesn't matter. So you have this term. Dividing it by e to the power of lambda ez, note that it's a positive number. It results in this inequality over here. Now you can use the Markov's inequality on this. So you have probability of z minus ez being larger than or equal to t, and this event is the same as this event. Now you can use the Markov inequality like this. You would divide it by this, which means multiplying it by e minus lambda t instead of positive. And here would be the expected value of e lambda z minus ez. Now, given that the value of lambda here doesn't matter, you can use any lambda value in order to bound this, as long as it's a positive, or sorry, non-negative lambda. Therefore, in order to pick like the sharpest bound, the best, tightest bound, you would pick a you would pick the lambda that minimizes this bound, therefore you would put the minimum here. An important fact about the Chernoff bounds is allowing you to play with the summations. So if you pick the summation of n random variables zi's that are independently sampled, for example, from a distribution, if you pick the moment generating function on them, you would end up with, so a moment generating function on the random variable, which is summation of some other random variables, would become the multiplication of the moment generating function of each one of them. Given that you have the expectation in the definition, therefore, expectation of summations to the power is basically similar to the multiplications. Therefore, you have this term. Now, what does it mean? Given that the zi's are independently sampled, you could pick only one of these random variables, moment generating function, and then just use the n. And therefore, for example, if you're looking at this probability, you can bound it like this. And yeah, it becomes like this. Because it's a multiplication, it's basically the same as computing it for 1 and just multiplying to the power of n. Let's consider some examples. Now, let's see, let's say z is coming from a distribution of Gaussian with the average of 0 and a standard deviation of sigma. Therefore, if you consider the e of e lambda z, it's going to be limited to e to the power of lambda 2 sigma 2 divided by 2. And the question you might be asking is, why is this true? Let's see why. Z is coming from n of 0 and sigma 2. Let's write this down. So you have the expectations, so expectation over the values of z of e to the power of lambda z, which basically all of the values of z are all of the r. So you pick a lambda like this. You are looking at this. Now you have to multiply it by the probability of z having that value, that specific value for z, which is this, based on the Gaussian distribution, 1 divided by 2p sigma 2, and just like this. Then you would expand it, and you will get 1 divided by, so you have this component here, you don't assume that the sigma is being changed, but the average is going to change over here. So 2 sigma 2 lambda minus c2, and you could write this entire thing as the integration over this term. So you could consider this the Gaussian with the same sigma times x of this term over here. Again, you have minus z2 minus sigma 2 lambda. Okay. Plus, so you have this term over here, right? If you add and subtract a lambda to sigma to the power of 2, you can get this component and get this component. So if you remove this out of the integration, you will have this term, and you also have this term being capped to 1. So yeah, therefore you do have this bound. So let's go over the Rademacher random variable. So you have S, which is a random variable which could take values of 1 or minus 1, and you want to say that the expectation of this is bounded by x above lambda 2 to the power of 2. Sorry, lambda 2 divided by 2. To see that, first let's take a look at the Taylor expansion of Ex, which can be written as basically summation from k from 0 to infinity of x to the power of k divided by k factorial. Now, if you take the expected value of s to the power of k, s again is the random variable which can take the value plus 1 or minus 1, you know that if k is even, the expected value of it is going to be 1 because whether or not it's 1 or minus 1, it's going to be like that. And if k is odd, given that it has the same probability distribution for 1 and minus 1, then the result is going to be 0. So you know that based on the k, if you have the random variable defined as s to the power of k, if k is even, it's 1, if it's odd, it's 0. Now, with that knowledge at hand, if you take the expected value of E lambda s, and then if you basically use the Taylor series expansion and then take the E inside because you have this summation, you will end up with the summation from k from 0 to infinity of the same thing. So you have k factorial here, but because the exponent is lambda times s, you have lambda times s to the power of k. Now, you know that it's only non-zero where the value of k is even. Therefore, you basically limit yourself to the even values by change of variables to 2k, and then you have this term. Expanding on this, there is this thing that 2k factorial is larger than or equal to 2 to the power of k times k factorial, which can be proven using induction. Consider this as a trick, as a lemma. Now, going back to this, we had this thing. So now we could actually know that, okay, so this 2k factorial thing is larger than or equal to this. So if you substitute the denominator with something that is smaller, then the value is going to get bigger. So you can have this, upper bound. So if you look at this expected value, it's upper bounded by this. Now you can bring this 2 inside, so you have lambda 2 to the power of lambda to the power of 2 divided by 2 to the power of k divided by k factorial, which is the Taylor series expansion of exp lambda 2 divided by 2. And therefore, you have this upper bound. An interesting question that we might be willing to answer is how big a sum of independently and identically distributed random signs is likely to be. So again, we are talking about the random variable s, which can take either value +1 and -1, and you could sort of interpret it as a random walk. Let's say 1 plus 1 is kind of going right and -1 is going left in some sense. And let's say you start from 0, and kind of you're trying to sort of see the probability of how much probability will be associated with you being like further apart than a distance from the average or something like that. So again, you have the random variable si's. So let's say each I is one of your steps, and you could see that like after I from 1 to n, you have taken n steps, which could be either forward or backward or right or left and things like that. So you have this new random variable defined z, which is a summation of the values of these things. So the summation of these random variables si's is going to give you z. Now you are looking at the expected value of z. Now, if you look at the expected value of z, it's going to be 0. Why? Because z was the sum of si's, so the expectation is going to go in, and therefore it's going to apply to each one of these individually, and it's going to be the expectation of summation is summation of expectations, and therefore because each one of these is individually 0, the result is going to be 0. Now if you look at the event of z being larger than or equal to t, let's say a positive number, this event, the probability of this event, we already know that it's less than or equal to this term over here. So it's less than or equal to e lambda z times e minus lambda t for a lambda, which you know from the Chernoff bounds. Now, consider this. Now, e times lambda s1 multiplied by lambda s2 all the way to lambda sn times e minus lambda t. Again, note that z was the summation, therefore you could have the summation in the exponent, meaning that you would have the multiplication of all of these. Which in turn means that you could consider one of them, given that these are identically distributed, and you have lambda times s1, you have this exponent here to the power of n times e minus lambda t. Now, note that we just showed that e of e lambda s is less than or equal to e lambda 2n, lambda 2, 2. Using this, we can get that there is the upper bound e lambda 2, 2 to the power of n, which becomes e n lambda 2, 2 times e minus lambda t. Now, we have this. Note that we have the positive values for lambda, and we can try to optimize it using that, given that the value of lambda didn't matter. So we go over the constraints. So lambda was supposed to be positive. Therefore, you want to minimize this exponent here, given that lambda is going to be a choice from non-negative numbers. All right, so you try to do this. And the way to do this is that, first of all, you have to note that x is an increasing function. Therefore, you take its inside, let's call it a. You want rho of a to lambda to be set to 0. And in this case, it will be n lambda minus t equals 0. Therefore, lambda optimal would be t divided by n. Then you would put this back in the equation. And what you will end up having is that you have n lambda 2 minus lambda t, which becomes minus t2 2n, given that this becomes t2 t2n and this one becomes t2 2n minus would give you this. Now let's say you want to talk in terms of probability delta. If you pick a t being 2n logarithm of 1 divided by delta, if you pick this t, then the probability of this summation being larger than or equal to this is less than or equal to this delta. So this is for when you want to talk in terms of probabilities. Let's say you want to find a t such that with the probability lambda, you are further than t apart in some sense from the average or from the 0. So in that sense, you can compute that t based on the probability that you desire. Something similar to, for example, let's say confidence bounds and things like that. Now what this means, if you look at this, it means is that the probability of 1 minus delta indicates that the summation of this SI with this probability, which is a high probability usually because you are sort of interested in, confident, close to mean things. With this probability, the order of magnitude, so the order in terms of n is going to be order of square root of n, or n to the power of half, for the summation of these SIs and its value. Now let us first prove the Hoeffding lemma, which means that if z is a bounded random variable such that z belongs to the closest span of a and b, then we want to show that this basically is a result of the lemma that for any lambda, which is a real number, this inequality holds, meaning that the expected value of the x of lambda times z minus ez is less than or equal to e to the power of lambda 2 divided by 8 times b minus a to the power of 2. To prove that, first let's see that for any lambda choice out of the real numbers, e to the power of lambda x is a convex function. Therefore, for any x in between the span of a and b, if you take the value of this function, gx is the same as e to the power of lambda times x. Gx is less than or equal to theta times ga plus 1 minus theta times gb, where this theta is between 0 and 1. Going over the span of a and b, you can define theta like this. So the length of the span is b minus a. If you define the theta like this, when x is equal to a, theta becomes 1, and 1 minus theta becomes 0, therefore you have ga. And when theta becomes, 0, that means this is becoming 1, meaning that you're looking at point x equal b, therefore you will still have the equality. Therefore, you have this inequality by substituting the theta and 1 minus theta, ga, and gb. And therefore, you will have this equation. Now we want to do something about this e of x. You can essentially, before starting this, you could essentially define x as x minus ex, which therefore results in that this new x of yours, the e of x, is going to be 0. It also has another advantage, which, given that x is a member of a and b, and the average of x is 0, that means 0 is somewhere between a and b. So going back from this result, you have this inequality. Now if you say that this is equal to a function of lambda b minus a, now if you look at this, so we said that this is going to be equal to this, and we want to find a suitable definition for L. Note that L, a function applied on lambda times b minus a, is equal to the ln of this term over here, which by factorizing e lambda a out of it, you will have e lambda a times this. Now add an a and subtract an a from the denominator of this fraction over here, and you can have this new equation, which of course you apply ln on e to the power of lambda a, and then because this is a multiplication, it becomes an addition here. So lambda a is brought out here, plus ln 1 plus, a minus a e to the power of lambda times b minus a divided by b minus a. Now, if we say that we want this L to be a function of h, meaning that h is going to be defined as lambda b minus a, you can pick a suitable choice for L by doing this. Multiply and divide by b minus a over here. So this term here becomes, this becomes h times a divided by b minus a. Note that definition of h was lambda times b minus a. So this becomes here. And then looking at this component over here, you could just basically substitute this part with h. With that definition, therefore, we have this definition for L of h. Now note that the value of this function at point 0 is 0. If you take the derivative of this function, the derivative of this function also at the point h equals 0 is going to be 0. Now if you consider the second derivative of LH, note that when you derived it the first time, you have this a divided by b minus a term here, which in the second derivative this part is going to be removed. Then this component of the derivative is going to be equal to basically minus a divided by b minus a, because you have this coefficient over here out of it. Note that this is the derivation like this. Anyways, when you bring this one out, you have this term. Now when you take the second derivative, you are deriving it with respect to h. Note that we removed the first component, so this is just the second component. If you derive it with respect to h, note that b minus a from the denominator of the first fraction gets cancelled out with the denominator of the other one. So you have minus a times eh divided by b minus eh a. And then you derive it with respect to h, you will have this right here, which if you look closely, this a times a eh gets cancelled with this component of this thing. So what you're eventually going to have is minus a b eh divided by b minus eh a to the power of 2. Now let's actually talk about the arithmetic mean and geometric mean inequality, but a simpler version of this. Let's say you have x equal minus aeh and y equal b. You know that x minus y squared is larger than or equal to 0. Therefore, x plus y squared minus 4xy is larger than or equal to 0. Therefore, xy divided by x plus y squared is less than or equal to 1 divided by 4. Which this means that for values of h, you have the second derivative being less than 1/4. Now you use Taylor's theorem, so LH is L of 0 plus HL prime of 0 plus 1, 2, H2 L second of 0. Sorry, fixing a mistake here. This is going to be epsilon or chi times h, where chi is between 0 and 1. This is based on Taylor's theorem or the second order mean value theorem, which states that there's going to be a point between 0 and 1 that if you multiply it by h and put it in here, this equality holds. And thus you can use the fact that these two are 0 and use the bound on the second derivative and limit the LH. And looking at this, with this Taylor approximation, this is going to be less than or equal to 1 divided by 8 times h squared. Now going back to this inequality, we can say that this is less than 1 divided by 8 lambda 2 b minus a 2. Now let's talk about Hoeffding's theorem, which states that if you have n independently sampled bounded random variables, meaning that if you combine all their bounds, you're going to have an a and b, which are going to be, this is minus infinity, a is a finite number, b is a finite bound, and less than infinity. All of these i's are going to fall between that bound. Then Hoeffding's inequality says that the probability of basically this 1 divided by n times summation of 1 to n of zi minus ezi, the probability of the event that this is larger than or equal to a value t for any sort of positive or non-negative t is going to be less than or equal this value, which is the e to the power of minus 2nt squared divided by b minus a squared. To show this, first we do the Chernoff bound technique and work with this probability. Start from the left side and take this n to this side of the equation. And we know from the Chernoff bound that you can basically write this as the expectation of, e to the power of summation of all of these lambda times ci's, and then you would consider them as multiplication of all these e's. Therefore, you have the multiplication from I to n of e to the power of lambda times ci minus eci times e minus lambda nt. Now, looking at this part, we know from Hoeffding's lemma that for the first component we have like this. So we had this bound from the Hoeffding's lemma. And note that now you can minimize this over lambdas. So if you actually do the minimization over these non-negative lambdas, you can actually ignore the e and try to maximize this exponent, which would result in lambda for b minus a2 derivative with respect to lambda being 0. Therefore, the lambda optimal is going to be nt4 divided by a2, which if you substitute, you are going to have, and forgive me, I forgot an n over here in this part. Therefore, in the optimal version of lambda, you don't have a n here. And therefore, by substitution, you have 2nt2 minus this equal minus 2nt2 b minus a2, which, given that e is an increasing function, the e of x is an increasing function, you could put that in there, get the optimal result, which is x of minus 2nt2 b minus a2, which is the Hoeffding's theorem. This finishes the proof for the Hoeffding's theorem, and on the other case, which is minus t like this, also the same sort of bound holds. And it can also be shown similarly.